overview, but I was working on a fuzzer for Unix, and I'll talk about it later. And anyway, when I was fuzzing it, eventually I hit this kind of bug in OpenBSD, and so that's in this function called AGPIoctal, and what they end up doing is they call AIX and some offset into it, and they reference it. And so I wonder what AIX would be. Oh look, it's a null pointer. And so what we end up doing is you map this page and you put a function pointer in there, and the kernel eventually calls it. So yeah, this one's exploitable. So that was the kernel. This was a demo. So this is not just theoretical. This really happens. You have to watch out with these kinds of things. So what about userlands? These things are, as it turns out, a lot more OS dependent than the kernel. In the kernel, we can still make some assumptions. On most architectures, we'll have this shared for address space, and you can map it. And so, it's not always true, but usually it is. In userland, it depends enormously depending on the operating system you're using. Your goal is still the same. You want to get an application to map the null page before it does any kind of null pointer dereference. I did most of my testing on Linux. I would assume there are similar cases in other operating systems, or maybe totally different cases where you can still end up getting a null page mapped. I did most of my testing on Linux. So first of all, in early 2.6 kernels, I think 2.6.9 till 2.6.12, they changed the way a userland application would get memory from the kernel. And basically, I think they call it a, top-down allocator. And what that means is, I'm just reading this stuff of LKML, right? I didn't make this stuff. But apparently what this means is that you start off with a very high address, in this case 0xbf something something something, and whenever you allocate memory, the address becomes smaller and smaller and smaller, and you go all the way back to the null page, including the null page. So what this really means is, if you have an application where you can get it to allocate arbitrary amounts of memory, eventually it will just map the null page, right? And so, you start thinking, what application could you, possibly get to allocate arbitrary amounts of memory? Oh, look, you have this browser, and, the more JavaScript you put into it and the more memory you allocate, it will happily do this stuff for you, right? So, if you're using one of these kernels and you think Firefox has a null pointer reference in it, be very scared. We're talking remote code execution here. Luckily, though, so this was actually talked about at a conference earlier, I think CanSec last year, and the kernel guy saw this and they're like, holy crap, something's horribly wrong, this can be abused, let's fix it. So they fixed it in Linux kernel where they would use this, basically they would keep the same memory allocator, but they would specifically exclude the null page from it. So if you would do this allocations and you would eventually get to the null page, it will just tell you you're out of memory. Bad luck, crash or whatever. But they basically said that they're still going to allow map fixed, which is good because that means you can still exploit kernel null pointer references. Because you want that, right? And this was done. This was actually done by Linus Torvalds himself. So if this doesn't work anymore, let's see what other options we have. Turns out on Linux, you've got this thing called personalities, and what that means is that you can say, hi, I'm an OpenBSD binary, or I'm an HP Unix binary, or I'm an SCO binary, or something like that. Emulate stuff for me so that I can work. This is called a personality. And one of these personalities is called SVR4. And for some odd reason, SVR4 binaries have to have the null page mapped, because if they don't, they go up in flames. So you say, hi, I'm an SVR binary, map the null page for me. And so what's really interesting about this is that these personalities, they get inherited through, every time you execute a new application, they get inherited. So as long as you don't change them, they stay the same. So you can say, hi, I'm an SVR4 application, and now I'm going to, run SU, and SU will be an SVR4 application as well, and the kernel will locate a null page in, for example, SU. So if then you have null pointer reference in SU, they might be exploitable. Let me get to that in a second. So these personalities get inherited, and this is basically the kernel code, and they basically say, why in the hell would you want to do this? Because SVR4 needs it, and if it's not there, it blows up. So, and that's why it's there in the kernel. And you can just call this, right? It doesn't do any kind of privilege check. You can do this for any application you want to, whether it's SUID or not. Right. So there's a downside to this feature in terms of exploitation. The null page is read-only. It's only null bytes on there, so it kind of limits the options. However, there's some good news. If you have 0x0000, you can see it as an alternative no operation on Intel, with the exception that AIX has to point to a valid address. They don't change it, but it gets referenced, so it has to point to a valid address. That's the only sort of constraint you have. So this thing can still be useful if you combine it with I talked about earlier, because you can get it to map the null page, and then you might be able to do a lot of allocations, and they would still locate the page right after the null page, right? And so if you'd have a function pointer that's set to null, it would go to your null page, which has all these nulls, which are alternative null operations. And the entire null page will just be NOPs, right? Goes to the second page where you do have control over it, and you'll have your shellcode in there, right? And so these things sometimes help in exploiting null pointer references. There are constraints. Sometimes this is enough. Right. So the last piece of null pointer references. Some operating systems also map the null page by default, but they don't allow you to read it or write it or execute it. So it's pretty much just there because they want it mapped, I guess. I don't know why. But it's useless to us because we can't touch it. It's there, but we can't touch it. There's one particular corner case which is exceptionally rare that I've been told they exist, where you have a null pointer reference, and before you actually do anything with it, they pass it on to mprotect to change the protection bits on this page. I've never ran into them. I've been told they do exist, these kind of bugs. So sometimes in exceptionally rare conditions, this happens. Okay, so the next one is, this was null pointer references. The next one is Stack Overflow. So I went out and, started looking for another nice code I could use for Stack Overflow. And so there's this, principal software developer for a company called Micro Focus. And I think this was supposed to do bug track, I agree that recursion overflow doesn't look like a very promising area for vulnerability research. And I'll tell you why he's wrong. People, as with null pointer reference, people go like, well, this is just another denial of service. But really it's not. If you think about it, a Stack Overflow is really just another overflow. You have a piece of memory, in this case your stack, and you write more to it than you're allowed to. This is a security bug, right? Writing more memory than you're allowed to is generally considered to be bad. So it's another overflow. The question you have to ask in order to get these things exploited is, can I force this application to map important data right after the stack, before you call Stack Overflow? And again, this is a question of context, and again, it's really operating system dependent, because the ways you want to try and force an application to map these things are really application dependent. But locally, the odds are in your favor, because you control the entire environment. You can say, I want my stack to only be this big, or I want my memory allocator to specifically use mmap instead of break, and then maybe it starts allocating pages right after the stack instead of somewhere else or whatever, right? So chances are, if you're doing this locally, that you can end up really exploiting these things. I did most of my tests on Debian stale. So Felix told me that you write it Debian stable, but you pronounce it Debian stale. So that's where I did my tests on. And this is an older version of the 2.6 kernel, where mmap data is not yet the top-down allocator, but they still have where it grows towards the stack. And it turns out that in the Linux kernel, there isn't a guard page between the stack and the heap per se. So what this means is if you can do enough memory allocations, eventually the stack and the heap are just right next to each other, right? This is stack, and you move one byte to the right, and oh look, I'm in the heap, right? Something like that. So basically, if you can allocate enough memory on the heap, and you get a stack overflow, you just end up writing into the heap, which is kind of bad, right? So that's a general case in Linux. Threads are something else, though. These are not really up to, in general, so there's a system call to do threads, but you don't want to do that because that's very operation independent. So you have an overlapping library called POSIX threads, which are, really well engineered and not over engineered, and they work exceptionally well, and there are no issues with that. But still, they're pthread implementation specific, these kind of things. And so what you do is you tell your kernel that, I want to be a thread, and this is going to be my stack, and use it. And then your libraries is responsible for either allocating or making sure you get a guard page or that you don't have them. So it depends on your library. I don't know outside of Linux because I only did Linux. Older glibcs do not give you a guard page. So what this means is if you have 2 or 3 threads, their stacks will be right next to each other. So if one of your thread has a stack overflow, it will write right into the stack of the next thread, which is again a really bad idea. Newer ones do. Newer versions of glibc, I think 2.2 or 2.3 point something, they have guard pages. So you would think that kind of stops these things, but it doesn't always stop them, right? You might have a function that looks like this, this here, where you declare a variable on the stack, which is as big or bigger as a guard page, and you end up not using it. And then you call some other function, and that means that you sort of just jumped over the guard page. And you might think that these things are not as common, but they actually are, because and maybe not you see these. Maybe you might not see these things in the actual application code, but I started digging around in libc code, and there's actually a lot of functions, at least in glibc, where they have this huge buffer on the stack, and then they don't use it, and they call some other function, and that function calls some other function. So if you could call any of these functions in one of your recursive functions, you could basically use or abuse your libc to jump over guard pages. I haven't actually tested this, but it looks promising. Again, the kernel, always with the kernel. Most in kernel stacks don't have guard pages. Because it's a waste of virtual memory, right? You can have an almost arbitrary amount of, these days anyway, an almost arbitrary amount of kernel stacks, and let's say if you'd have 1,000 and each one of them would need a guard page, then you're wasting huge amounts of virtual memory. And that might be okay on like 64-bit architectures, but it's a horrible idea in 32-bit architectures because the kernel usually only has very little virtual memory that they can actually use for memory allocations and in 32-bit architectures these days. So if you can, basically it's the same thing applies. If you can force some allocation before or after your kernel stack to be mapped, then they might become exploitable. Depending on whatever architecture you use, it's before or after. So I did a few tests on Linux, nothing that extraordinary, but it turns out that this is actually quite easy on Linux. And I didn't have to look far. Somebody else already did this for me. It's this guy called Polestar Zets. He's a Polish guy. He's exceptionally clever, and he's done a lot of Linux kernel exploits. And so in one of them, he needed to have exactly the same thing that I wanted to have. Is he wanted to have something after or before your kernel stack that you could smash into. And so, as it turns out, the Linux kernel basically has sort of a pool of kernel stacks. And so he worked out this way where he can basically say, if I'm this process and I want to smash into something after my stack, then if I do this, this, and this, which he describes here in short, then I can exactly determine what will be right after my stack and see exactly what I want to overwrite. So this works fairly reliably, this method. Although I do think that this particular method actually requires AOut to be used, and I know recent 2.6 kernels actually don't have it on by default anymore. So you might have to look into a few, change some of the details. But the basic idea is sound, basically, right? So what you do is you have three processes in userland, which you have three